Okay, we're on page 9 of the notes, and this is on graphical solutions of trigonometric equations. So many trig equations cannot be solved by algebraic methods, particularly if part of the equation has trigonometry and another part of the equation has either algebra or exponentials or logs or something like that. So an equation like this one here that I've just highlighted, you can't solve that by any algebraic method. Likewise, this equation here, you can't solve it by any algebraic method because it involves trig and algebra together. Okay, so for these type of equations that I've highlighted, approximation methods are used, and for us, because we can't use computers, we graph. Okay, so graphs can usually be used instead, and what the graph will show. Number one, the most important thing that we're often after is just how many solutions there will be. And remember, the solutions are given by the points of intersection. So how many solutions, how many points of intersection. And you can sometimes guess or get a good idea of what the approximate value of the answer is, particularly if you draw your trig graph to scale very well. Okay, so let's do first question. On the same graph, sketch y equal 2 cos x and y equal log to the base e of x for the domain 0 to 2 pi. Okay, so let's draw, going from x is 0, so I'm going to put my graph on the left hand side. Draw your graph nice and big. Okay. Now for cos 2 cos x, the period is 2 pi. Important points happen, period divide 4, so every pi on 2. So the basic cos graph, we know how to draw that. So I'm going to put pi on 2 there. I'm going to try and draw a consistent scale, pi, 3 pi on 2, and we're going to 2 pi. Okay, cos starts off at 1 and then goes down, but there's a vertical dilation factor of 2. So we're actually going to start from a height of 2 and then go down. I need to try and be consistent. My y-axis scale here, -1, -2. So down, and then at pi it'll be -2, 3 pi on 2 it'll be 0, 2 pi will be back up at 2. So that's what the cos graph looks like. And now we need to draw, so that's y equal, I'll label it 2 cos x. Now we need to draw the other graph, y equal ln x. Okay, remember the two key points for the ln or any kind of log graph is it always has an x-intercept of 1. So pi on 2 is about 1.5 something. 3.14, so half of 3.14, 1.57-ish. Okay, so if I wanted to do 1 would be about there. And we know it's going to cross the x-intercept there. We've got an asymptote for the log graph. We should show that of x equals 0. And we know that every time we know that ln e is 1, and we know that, so that's our second point. Our second nice point is e comma 1. So e, remember, is about 2.7-ish. So 2.7 is a bit below pi. E would be approximately there, a height of 1. We have our second point. Okay, I think it would be good to work out what the ln graph will look like at the end. So let's substitute in when x is 2 pi and see what we get. So when x is 2 pi, we get ln 2 pi, and that is approximately, I put in my calculator, 1.84 to 2 dp. So we're below the 2 mark here, we're 1.84. Okay, so I'll label that endpoint, and I should have labeled the other endpoint there for the trig graph, 2 pi comma 2, and this one's 2 pi comma ln 2 pi. Okay, so I think I've got enough here to draw. There's my graph. I'm going to put an arrow approaching the asymptote. So there's my log graph and there's my cos graph drawn on the same one. So hence state the number of solutions in the domain 0 to 2 pi. Okay, so in the domain 0 to 2 pi, we're looking for intersections. I've got one intersection here that's somewhere between an x value of 1 and pi on 2, and I've got another intersection here, somewhere between 3 pi on 2 and 2 pi. So there are two intersection points, so therefore here and here, and there are two solutions. So state the number of solutions. There are two solutions in domain 0 to 2 pi. If we kept the graphs going, you might actually find that there's more solutions than two if we allowed it to continue in the domain. But in the domain 0 to 2 pi, there are two solutions. Okay, next question. Sketch y equals sine x for negative pi to pi. That's actually already done for you. And y equal mx for m being 1, a half, and negative 1. Okay, so all these graphs have a y-intercept of 0, and we're just drawing different gradients. Now, I think so the easiest way is to plot a few points here. For a gradient of 1, so it's just y equal x. When x is pi on 2, the y value will be pi on 2, which is about 1.57. So 1.246. So 1.57 will be about here. And when x is pi is 3.14, so it'll be about there. And negative pi on 2, the y value will be negative 1.57, so just above negative 1.6. And negative pi, it'll be about there. Okay, so we need to draw a line connecting these points. Now, if you remember when we're sketching the basic sine graph, it crosses the x-axis with a gradient of the tangent of being 1. So actually, if I'm drawing y equal x, it should be a tangent. It should be a tangent. Should be, I'll try doing that again. It should be a tangent. It should just touch there and keep going. Not a brilliant effort on my part. I'm not going to put arrows on this line because it's got to be between, oh well, it doesn't say the domain for mx, but we'll keep the same domain here. Okay. I'll add 4 negative pi to pi. Okay, so no arrows then. Okay, so it's a bit hard to see here, but because I know that the gradient of the tangent of y equals sine x is 1 at the origin, and this has a gradient of 1, it's only going to touch once. So this particular line y equal x and y equals sine x only touches once at the origin. So I'm going to label y equal x. Next one is going to be m equals a half. So that'll be y equal half x. So I've got to half the values. I think the easiest way of doing it is if I half pi, I get pi on 2, which will be here. That'll be a point. I know it goes through the origin, and if I half the pi, negative pi, you get negative pi on 2, which is about here. Okay, so I'm going to try and draw with just those 3 points. And hopefully we can see that that crosses at 3 different parts. Okay, one with negative x values, one with positive x values, and one in the middle. So that's y equal half x. And the last one, negative 1. So we should be able to draw that pretty quick. Gradient of negative 1. So that'll be negative 1.57-ish. Okay, that'll be height of negative 1.57. That one there, negative pi. Okay, something like that. Okay, so I'm going to label that negative x. So hopefully we can see the y equal negative x graph is just going to hit once at the origin. Alright, last question. How many solutions are there to sine x equals mx for between negative pi and pi? Now, we're obviously going to be using the graph that we've got above here. Let's start off with negative gradients. So let's imagine m is negative, if m is negative, if you drew any negative line going through, I hope you can see that it's only going to touch the origin only. So if m is negative, so for m less than 0, there'll be one solution, x equals 0. Now, let's imagine if the gradient equals to 0. So if the gradient equal to 0, there would be 3 solutions. There would be the 2 endpoints and the origin. And also, if I slightly increase this gradient, hopefully you can see that it's going to cross at, there's going to be 3 different points. There'll be one on this branch, one on this branch, and one at the origin. Okay, so it appears that as we go from 0 and we start increasing slightly, there's going to be 3 solutions. Okay, so if we are equal to 0, and we'll have a think about what that number on the right, there'll be 3 solutions. Okay, one of the solutions will be x equals 0, and there'll be one that's negative and one that's positive. Now, remember, we drew our y equal x, and we said that that was a tangent to the graph and at the origin. So therefore, it actually only, y equals x touches only once. So I'm going to put a 1 there, because we know that a gradient of 1 will touch once. There'll be one solution. And convince yourself that any gradient bigger than 1, think about gradients greater than 1 now. If I drew a line which was steeper than 1, convince yourself that it will only have the one solution, x is equal to 0. Okay, so any gradient that is 1 and higher, okay, any gradient that is 1 and higher will only touch that sine x curve once at x equals 0. So that covers all possible gradients. So less than 0, there was one solution, x equals 0. Greater than or equal to 1, there's one solution, x equals to 0. And if it's between 0 inclusive and 1 not inclusive, it will touch 3 times. Once at x equals 0, and once for a negative value of x, and once for a positive value of x. Alright. What I'd like you to do now, complete exercise 12.3. Those questions, and then complete, there's just 2 more questions from 15.6 to ENF that won't take long.